Thank you very much for the introduction, and thanks to the organizers for the invitation. So as we all know, we're here to celebrate the achievements and the huge career of Rick Kenyon. I've had the privilege of being a Rick student, and when I did my PhD, I quickly noticed, that people would associate Rick's name with the diamond model. So they would ask me, are you working on the diamond model? Well, no. I was doing my PhD on geometry, on circle patterns, and back then there was no direct connection with diamond models. So I think that the official title of the conference is rather appropriate because it gives a hint of the span of Rick's interest. Rick has been creating connections between very different areas of mathematics, and we could even add a few more areas. But I must admit that often, not always, in the background you have tilings and dimers hidden. So here they are hiding at the very beginning of the title. And after my thesis, we realized in a paper with Rick and also with Wayne Lamb and Mariana Ruskir that there was a very close connection between circle patterns and diamond models. Beyond creating connections between areas of mathematics, Rick has created a lot of connections among people themselves. Because Rick, you have been talking to mathematicians and even physicists and computer scientists in very diverse areas, and you've brought all these people together, actively building a community, as evidenced by the crowd here today. So most of the speakers this week are going to discuss one aspect of the many achievements of Rick and show how their own work is building upon this. And I'm taking a different approach. I will discuss something on which Rick hasn't worked yet, but I believe, knowing your mathematical taste, that this is something that you would like. I hope so. And I hope that that's something that you might be working on in the second part of your career. So I'm going to discuss some joint work with Bastien Mallein and Arvind Singh, as well as Benjamin Terlat, who was my PhD student. And it's about the infinite bin model. So infinite bin models are a family of interacting particle systems indexed by a probability distribution, mu, on the set of positive integers. In this big family, for some special choices of mu, you can find connections to branching random walks. For other choices of mu, you can find connections with last passage percolation. And you can imagine that this particle system is like a cloud of particles drifting to the right. And there are like two natural ways to look at it. Either you fix one location, and while the cloud is moving to the right, you keep looking at this location. Or you imagine that you are sitting on top of the front of this cloud of particles, and that you are moving to the right at the same speed, and your window of observation is also moving to the right at the same speed. So then you would be looking at the scenery from the front. This scenery from the front is now rather well understood, but if you look at a fixed location while the front is moving, we have now some partial understanding, but not complete yet. And one thing that we've done recently is to introduce an exactly solvable hydrodynamic limit of the model, where we have nice phenomena like wall crossing phenomena, and there are also some nice structures from algebraic combinatorics that are showing up. So that's what I will be discussing throughout this talk. So what's the model, infinite bin models? The configurations, you have infinitely many bins indexed by z, and each bin may be either empty or contain a finite number of balls, or contain infinitely many balls, as in this bin here, these 3 dots indicate that you have infinitely many balls in this bin. But I require that there is a property that these configurations should satisfy. There should be a rightmost non-empty bin. So to the right of this bin, everything is empty. And this is called the front bin. Then we are going to define some dynamics on the space of configurations. For every positive integer k, we define a move of type k. What does this mean? You count your balls from right to left, starting at the front, and you find the kth ball. So here, if k equals 5, the 5th ball, so you count 1, 2, 3, 4, 5, the 5th ball is in this bin, and a move of type 5 adds a new ball immediately to the right of the 5th ball. So here you see that I counted the balls from bottom to top and right to left, but you can break ties in the way you want. There is not a specific way in which you should count. You will still end up in the same bin for the kth ball. So a move of type k takes as an input one configuration and outputs another configuration. In this example, you see that the front did not move. It remained at position 2. But if now I apply to the same initial configuration a move of type 1, so a move of type 1, the first ball is always in the front bin, so it will always create a ball in a new bin. So when you do a move of type 1, the front always advances. And here, if you did a move of type 2, it would also advance. So that's the dynamics that we do. And now we're going to make this dynamics stochastic. So what we do is that we have two inputs in our model. We have an initial configuration, and we have some probability distribution mu on the set of positive integers. And we sample an IID sequence, xn, which is distributed like mu. For example, 1, 4, 3, 9. And starting from x0, we do first a move of type 1, then a move of type 4, then a move of type 3, then 9, and so on. So it's this Markov chain that is called the infinite bin model with moves distributed like mu. It was defined for the first time by Foss and Konstantopoulos in 2003. And what is the most interesting observable in this model is the speed of the front. The speed of the front is that you look at the position of the front at time n, and by how much it has moved since time 0, and this position increases linearly with n at a rate that we call the speed v mu. So it's almost surely constant, and it is independent of the initial configuration. It depends only on the probability distribution mu. That's something that Foss and Konstantopoulos proved in the case when mu has a finite first moment, and with Bastien Mallein we proved it for every mu. So one question throughout the talk will be, are there some classes of models for which we can compute mu? And if so, how? So let's see some nice examples of mu.
Sorry, what was the initial condition?
You take any initial configuration. So it's just the definition that I had, balls in bins such that there is a well-defined front.
No finite or infinite?
It could be infinite. It doesn't have to be finite. And yeah, the speed does not depend on the initial configuration. Yeah, please stop me if you have any questions throughout the talk. So let's start with this special case of the uniform distribution. So you fix one integer n, and you look at the uniform distribution on the integers between 1 and n. In that case, the infinite bin model with move distribution mu is related to some branching random walk with selection. More precisely, it's the pure jump process of a continuous time branching random walk on Z with selection of the rightmost n individuals. So what does this mean? It means that you have n particles on Z, here n equals 6, And each particle carries an exponential clock, independent IID exponential clocks. When the first clock rings, for example, the clock of this particle, it will reproduce, and it will have a child one place to its right. So now you have n plus 1 particles, and you have the selection process, which kills the leftmost particle. And this is the same as the infinite bin model with uniform distribution, because only the first n particles are allowed to reproduce, and that's why we are killing the n plus first particle. And this was first studied by Audos and Pittman even before the introduction of the general infinite bin model in 1983. And they showed that when you take the limit n goes to infinity, the speed of the front grows like e over n, e being exponential of 1. And so here you see that when mu is the uniform distribution on 1n, it's related to a branching random walk with selection. But when mu is general, you can say that the infinite bin model is a rank-biased branching random walk. Because here you see that every particle has the same reproduction rate. But in general, the reproduction rate is biased by the rank, where the rank is counted from the front. Now, second special case, it will be when mu is a geometric distribution. In that case, it's related to the so-called Barak-Erdős graphs. What are Barak-Erdős graphs? So you fix an integer n, here n equals 6, and you fix some parameter p between 0 and 1. The vertices of the graph are the integers from 1 to n, and for every I strictly less than j, with probability p, you add an edge directed from I to j, and with probability 1 minus p, you don't add any edge. And this independently for each pair ij. So you get something like this. And okay, what you get is a directed acyclic graph that was introduced by Erdős in 1984. They were looking, when they introduced this, at independent sets of the graph. But quickly after that, people started looking at the length of the longest path in these graphs. And this was a question that arose in many fields. I'm giving an example, several examples below. In computer science, for performance evaluation of parallel processes, in mathematical ecology, where it represents food chains, and in queuing systems. So the length of the longest path, you know, you are counting the number of edges in a longest path, because there may be multiple longest paths of the same length. In this example, you have 2 longest paths of length 3. And this was studied in detail by Newman in 1992, who showed that the length of this longest path grows linearly with n, and the constant c depends on the probability p of an edge being present. And I don't know why I didn't write this in these slides, but you probably noticed that if you remove the direction of each edge, what you get is nothing but an Erdős-Renyi random graph. So it's a directed acyclic version of the Erdős-Renyi random graph. So you have this constant for the linear growth rate of the longest path, and it's a function of p. And the way it's defined, you know, it's defined by subadditivity. So it's very implicit. And there has been a lot of work since 1992 to find explicit properties of this function c of p. So that's a plot of this function. Wait. Yes, it comes afterwards. So this Barak-Erdős graph model is coupled with the infinite bin model, where mu is a geometric distribution. So I define mu p. So it's the same p here as for the Barak-Erdős graph, the probability of an edge being present, as the geometric distribution on the set of positive integers. So the probability of k is p times 1 minus p to the power k minus 1. And the coupling is such that the speed of the IBM mu p, so it's v mu p, it's equal to the growth rate of the length of the longest path in the Barat-Kadosh graph. So the two observables of interest in each model are equal to each other. And that was a coupling that was introduced by Foss and Konstantopoulos in 2003. And actually, that's how they ended up defining the general infinite bin model. They generalized this from geometric mu to arbitrary mu. So as I was mentioning, the interesting part about C of P is to find some properties of it, even though it's defined implicitly. So Newman showed that C is a continuous function on 0, 1, and it has a first derivative at 0, which is equal to e, exponential of 1. And it's the same e, if you remember, as in Auder-Spittman. Foss and Konstantopoulos found a 5-term expansion around p equals 1. And so I'm a combinatorialist. When I see this, I see that there are only integers. And the first thing I'm asking is, can you find the full expansion with only integers? So that's what got me interested in this problem. And we worked on this with Bastien Mallein, like 5 to 10 years ago. And we generalized Newman's result and Foss and Konstantopoulos' results. So we showed that for p strictly positive, C of p is an analytic function of p and can be written in some way as the sum of a series. But the analyticity doesn't extend to 0 because around 0 we have the following asymptotic expansion. We have 2 terms and a conjecture for a third term. And the second term in particular, it's in p over log p squared. It says that you don't have a finite second derivative. And the way we prove this actually, this E, we really make a direct connection to the infinite bin model with uniform distribution of Auder-Spittman. That's why I'm saying it's the same E. And that's also Newman's E, C prime of 0 equals E. So that's around p equals 0. And around p equals 1, we show that there is a power series expansion that has only integer coefficients. So it's really a general feature that all the coefficients are integers around p equals 1. And so we still have several open questions here. So this sequence of integers around p equals 1, I've written the first few terms here. And you see that they're alternating. And the natural conjecture is that this was a sequence of alternating signs. But my former student, Benjamin Terlat, managed to compute 40 terms, and he found out that starting at the 28th term, it's no longer alternating. And that's a general feature. If you look far enough, you will see that it is not an alternating sequence, but most of the time it's alternating. So it's a very tricky sequence. So we've added this sequence to the OEIS. There are now like 45 terms. You can check. It's this sequence. And a natural question when you have a sequence of integers is, can you find a combinatorial interpretation of these integers? At first, when we thought that they were alternating sign, you can just say it's a positive sequence and with -1 to the power n in front. And you just want to count, you want to understand what these positive integers count. But now that we really have a sequence of signs that may vary, it's a question which is a bit more tricky. But now there are some tools, for example, in the ASM community. People are looking at signed bijections, zijections. So the question, I could reformulate it like this. Can you find 2 collections of sets, AN and BN, such that these integers are equal to the cardinality of AN. The nth integer here is cardinality of AN minus cardinality of BN. And it may look like a random guess, but at some point I did a perturbative expansion for this Barat-Kadosh graph, and I found essentially some kind of interpretation in this direction, but it worked only until the 8th term. And I'm hoping that one can fix this to get an interpretation of the entire sequence. And another big question is whether one could find some explicit characterization of C of P, either some direct formula or some differential equation satisfied by it, or some functional equation satisfied by it. So here again, it may look like a wild question, but I've had some discussions with people at IPHT who told me that in supersymmetric Yang-Mills theory at n equals 4, you have similar functions that have an asymptotic expansion on one side, like the one we have at p equals 0, and on the other side at p equals 1, something with only integer coefficients, and that you can write them as a combination of special functions. So I'm thinking that maybe there is something behind here too.
Sorry.
Yes?
When you say that there is an implicit equation for C of P, what kind of equation is it?
I don't know. Can you find a function?
No, you said there's already an implicit equation.
No, I didn't. When did I say that?
How did you plot C of P then?
Well, C of P, you can see it as appearing in two probabilistic problems. So you can just sample, either a Barak-Erdős random graph and look at the length of the longest path, or sample an infinite bin model with geometric distribution and compute the speed by just some simulation.
Oh, I see. So the graph is purely,
Yes.
the plot is purely simulation.
Simulation, yeah.
I see.
Yes, Rick. Rick?
So how do you compute the 24th coefficient and show that it's an integer?
So there is a formula as a sum of a series that I will show in a few slides, but it's not so I will discuss that. But to answer your question for Foss and Konstantopoulos, it was a different method. They found an upper bound and a lower bound. And actually, that's one of the good methods to find these coefficients. You find upper and lower bounds that coincide for many terms for the asymptotic expansions. You approximate your geometric by truncated geometric, and you already get very good results like this. Other questions?
Yeah,
Yes.
Is the absolute value of the sequence monotonically increasing?
That's also a conjecture we had, and I think that's also wrong.
That's also wrong.
Yeah.
Oh.
But not by a lot. I'm not sure about that. I would need to check. Okay, let's move on. So there are some extensions of this coupling between Barak-Erdős random graphs and the infinite bin model with a geometric move distribution. So you can generalize Barak-Erdős random graphs to last passage percolation on the complete directed acyclic graph. So you pick a probability distribution mu on the set of real numbers and minus infinity, which has a finite upper bound for its support. And then you look at the complete directed acyclic graph on the integers, and you attach to each edge an IID weight distributed like nu. And you define the weight of a path to be the sum of the weights of the edges along the path. And here again, the weight of the heaviest path grows linearly with the number of vertices, and we denote by C nu this linear growth rate. So usually when you do last passage percolation, you have weights that are positive numbers. You don't allow negative numbers or minus infinity. And in that case, you can interpret this positive number as the time it takes for a liquid to cross this edge, and the constant C nu is called the time constant because it corresponds to the last passage time of this liquid through this medium, this porous medium. But we allow negative weights and even minus infinity because with this, Barak-Erdős graphs are just last passage percolation on this complete graph with weight 1 with probability p, or minus infinity with probability 1 minus p. Because if you have an edge of weight minus infinity, it means that your whole path has weight minus infinity, so you're killing this path. And we showed with Foss, Konstantopoulos, and Mallein that for general mu, there is also a coupling with some interacting particle system. This time it's not on z. The positions of the particles may be real numbers, positive real numbers, and the speed of the front of this particle system is equal to c nu. So you see that this geometric infinite bin model has generalizations in two directions. Either you generalize it to the infinite bin model with arbitrary move distribution, or you generalize it to this interacting particle system that we call the max growth system. So how, that was a question of Rick, how do you prove these properties about C of P if it's defined implicitly? So for this we need to understand how to describe the scenery seen from the front. And for this, we want to construct a stationary process. So the infinite bin model was for positive times. You start at time equals 0 with an initial configuration, and then you construct all your configurations for positive time. But we want to do something different. We want to consider a process with time indexed by z, positive and negative integers. And then it has no starting configuration. Morally speaking, your starting configuration is at time minus infinity. So what I do is I give you a bi-infinite sequence of integers, xi n, that are distributed like mu. And just seeing the sequence of integers, can you tell me what my configuration is at time 0? So you know all your moves at negative time. What is the configuration at time 0? And so it's a sequence that should satisfy this recurrence relation, which is the same recurrence relation as for the IBM. But you don't have the starting configuration at time 0. So this is actually possible to do this, but when you reconstruct x0, you will reconstruct it up to a global shift because you don't know where's the position of the front. But you can still reconstruct it. So I will show you like a toy version of this. So I will explain to you how to reconstruct the content of the front bin, but it's something similar to reconstruct the entire configuration. And I will also assume, for simplicity, to avoid technicalities, that mu of 1 is positive and that mu has finite expectation. So in that case, what do you do? In that case, you can consider, following Foss and Konstantopoulos, triangular sequences of integers. So it's a finite sequence of positive integers, u1, un, such that the ith entry is at most I. So for example, 1, 1, 3, 2 is triangular, but 1, 3, 2, 4 is not, because the second entry, 3, is greater than 2, the position. What is nice about triangular sequences is that whatever your initial configuration is, so here I'm giving two examples of possible initial configurations, the place where you're going to position the new balls is independent of the starting configuration. It only needs to know where is the front of this initial configuration. So in both configurations, the front ball is at position 0. That's all you need to know. And then suppose you run the sequence 1, 1, 3, 2. You place the new balls exactly in the same way. So now that you know that, recall that I gave you the sequence of moves from minus infinity to 0, and I'm asking you to reconstruct the content of the front bin. So you go back in time, starting from time 0, until you find the first time when you have a triangular sequence between that time and 0, starting there. And because I assume that mu of 1 is positive and mu has finite expectation, this happens almost surely in finite time. So you denote by t this time, and whatever the configuration is before this time t, after applying the sequence of moves, the content of the front bin will be the same. And you define this common content to be what is inside your front bin at time 0. So yeah, it will be if you have this sequence of move, this is where you have your first triangular sequence starting before time 0. And you can say what is in the front bin. So now I'm going to define triangular minimal sequences. If you have a sequence which is triangular, if it has no strict suffix which is triangular, then I call it triangular minimal. For example, 1, 2, and 1, 2, 2 are triangular minimal, but 1, 2, 1, 2, 2, it is triangular, but it is not triangular minimal because you can find a suffix of this word, 1, 2, 2, strict suffix, which is triangular. And what you observe is that when you go back in time and you find the first time where a triangular sequence starts, what you cut out is a triangular minimal sequence. So using that, we can get a formula for the speed of the infinite bin model, or the front of the infinite bin model. So for this bi-infinite stationary version of the infinite bin model, the speed of the front is simply the probability that at time 0, the front advances by 1 step. And that's again something that you can read from this sequence between minus infinity and 0. So we define Tm plus to be the set of triangular minimal sequences such that the last move makes the front advance. For example, if you look at these two triangular minimal words, sequences, 1, 2, 2, and 1, 2. So 1, 2, 2, I'm going to run it on the left here, 1, 2, 2. The last move makes the front advance. But if you run 1, 2 on the right, 1, 2, the last move does not make the front advance. So 1, 2, 2 is in Tm plus, but 1, 2 is not. And the speed formula is given here. It is the sum of sequences in Tm plus, sum over these sequences of the weight of the sequence. So what is the weight of a sequence of integers? It's simply the product of the probabilities of the integers on the mu. So on the one hand, it is a formula as a sum of a series, and it is explicit enough to prove the analyticity of C of P and to compute many coefficients of C of P. But on the other hand, there is no simple characterization known of this set Tm plus. And actually, we have many formulas. We have also sums over other sets of sequences. But it's never something very explicit. So I'm still looking for a more explicit formula for C of P. So yeah, we can generalize it even when mu of 1 is not positive or when mu doesn't have a finite expectation. That's something we did with Bastien Mallein. And more generally, we can do perfect sampling under the stationary distribution of not just the content of the front bin, but any finite dimensional marginal seen from the front. And this is a procedure that is very similar to the coupling from the past procedure that was introduced by Jim Propp and David Wilson. So that was understanding the scenery seen from the front. Now let me take another perspective and try to fix one location and understand how the content of a fixed bin evolves as the front moves to the right. And that's joint work with Bastien Mallein and Arvind Singh. So we fix k, some positive or negative integer, and we look at bin number k. The content of bin number k keeps growing. It's a non-decreasing sequence. And you can define x infinity of k, its limit when time goes to infinity. And the question is it finite or infinite? We say that the kth bin freezes if this final number is finite almost surely. And we want to find conditions. So we have two parameters. We have our initial configuration, and we have our measure mu. When we were looking at the scenery seen from the front, the initial configuration did not matter. Everything depended only on the measure mu. But here, things will depend both on the initial configuration and on the measure mu. So one first remark that I can make is that if you have a starting configuration which is uniformly bounded, meaning that in every bin you have a finite number of balls, and you also have a uniform bound, m, on the number of balls in every bin, then every bin freezes, whatever the measure mu is. But you want something more general. You want to allow so-called locally finite initial configurations. Every bin contains initially a finite number of balls, but you may have a number of balls that increases as you go towards minus infinity. In that case, do we still have freezing or not? Well, now it depends on you and on the initial configuration. So to solve this question, we are going to compare this arbitrary locally finite initial configuration to a test initial configuration, which is extremal in some sense. It's an infinite column. Let's say I place it at position 0. And once you have an infinite column, you just need to know where is your kth particle for every k. So in that case, it will be always at bin 0. So you don't need to know what is to the left of that column. You don't see what is to the left of that column in the infinite bin model. So you just have an infinite column, and we define a measure to be of type k if, starting from this infinite column, it produces k minus 1 infinite bins and then finite bins. Infinite column. If it produces a cascade of k minus 1 infinite bins starting from a single infinite bin. So the definition is a bit abstract. Can we have some concrete examples of what is a measure mu of type k? So type 1, there's a very simple characterization. Mu is of type 1 if and only if it has a finite first moment. So if you have a measure which has finite first moment, you apply it to an infinite column, it will always produce finite bins. Then if your measure mu is regularly varying of index minus alpha, so that's the definition of regularly varying of index minus alpha. The intuition behind it is that mu of j, the sequence mu of j, behaves like j to the power minus alpha. That's the leading polynomial term, and then you may have some corrections, like logarithmic corrections, for example. If your measure mu is regularly varying, then you can explicitly compute its type. I'm not saying how, but there is an explicit description in the paper. And in particular, if it is regularly varying of index minus 1, then it is always of infinite type. So what's an example of regularly varying mu of index minus 1? It's if mu of n equals 1 over n times log of n squared times a constant. So that's an explicit example of mu of infinite type. So then we have the following dichotomy. If we have mu of finite type k, and I'm also assuming that the sequence of probabilities mu of j is non-increasing, then every bin freezes regardless of what the initial configuration is. So here we need to assume this non-increasing condition for technical reasons, because to be able to compare the initial configuration, which is this infinite column, and our arbitrary initial configuration, we are constructing a coupling between the two infinite bin models, starting from these two initial configurations. And this coupling, we managed to do it only using this technical condition that we could relax to ultimately non-increasing, but still there has to be some technical condition here. But maybe we can come up with a different proof for other mu's. And that's when you have finite type. But when mu is of infinite type, then you can find some locally finite initial configuration such that every bin goes to infinity. So in particular, if you take this mu to be like to grow like 1 over n log n squared, then you will create only infinite bins if you take a starting configuration which has bins that grow fast enough to infinity as you go to the left, to minus infinity. So it means that these mu's of infinite type, they remember the starting configuration. They remember something of the starting configuration. So it's a long memory process, this infinite bin model. So I started a bit late, right? I'm getting to my last part. So when you see the definition of the infinite bin model, I like exactly solvable systems. So I'd like to find some classes of mu's for which I have an explicit expression for the speed of the front v mu. So what can I do here? First, if your measure mu has a finite support, as you saw, for example, when you have the uniform measure on one n, then you can reduce it to a Markov chain on a finite state space. So in theory, you just need to find the stationary distribution of a finite state space Markov chain. So you can do it in theory. But the number of states is exponential in m, the upper bound of the support. So it quickly becomes intractable. The other idea that we've had with Benjamin Terlat is to fix the number of elements in the support of mu, and you make them grow to infinity linearly. We take a hydrodynamic limit. Let me explain on an example what we are doing. So suppose your measure mu has a support of size 2. With probability p, it takes value 2n, and with probability 1 minus p, it takes value 3n. And n will go to infinity. The first thing that you notice is that in your front bin, you need to have at least 2 n balls before you can create a new front bin. And so the speed of the front, so the time it takes to create a new bin grows linearly with n. So the speed is in 1 over n. So we need to rescale the speed of this by n when we take n to infinity. And we find a nice limit. It's a rational function in p. But now if I change slightly the example, I have n with probability p instead of 2n, and 3n with probability 1 minus p. Then after rescaling, my limit has a different behavior. It is piecewise rational. So what you see here is a function that is rational between 0 and a half, rational between a half and 1, and it is continuous at 1/2, but it is not analytic. So this is some sort of phase transition in this hydrodynamic limit. And we would like to understand this when the support of the measure mu is finite but larger than 2. How to describe this? So we take now k elements in the support. So we take positive numbers, a1 to ak, ranked in the increasing order. And again, k parameters pi, that sum to 1. And we look at this probability measure mu. We have n times ai with probability pi. The ai's don't have to be integers. They can be just positive real numbers. So we need to add some floor here to make sure that these are integers. And what does the infinite bin model do? So here, if k equals 3, there are 3 locations that are singled out in the configuration. This would correspond to n times a1. And we are going to add balls to its right at rate p1. So the expected number of balls that you add to its right is p1. And since this bin contains both the ball of rank n a2 and n a3, you would add here balls at rate p2 plus p3. So this gives you a hint of how to define the hydrodynamic limit. Instead of having balls inside bin, you're going to have liquid inside bin, and you're going to have a continuous time deterministic evolution of liquid inside bins. We call this model the liquid bin model. And we have these parameters AI and PI, and we are going to place inside each bin, we are going to place a cursor, the ith cursor, associated with AI. So for this, now I really count the balls, from bottom to top in each bin. So I'm placing the cursor here in such a way that below it, here, and to its right, I have A1 units of liquid. And similarly, if I look below this green cursor, below it, and all the way to here, I have A2 units of liquid. And I'm going to add liquid in the bins where you have these arrows at a certain rate pi. So to the right of cursor I, I'm adding liquid at rate pi simultaneously for all I. The system is called stationary if when you start from some configuration, no, it's called stationary if when you start at time 0 from a certain configuration, after some time t, your cursors, were somewhere at time 0, they are moving, and at time t, they will be exactly at the same location, but just translated by one bin to the right. And now is the technical part of the talk. Oops, how do I get out of here? Escape. Is this? Okay. So don't look at what is written all around. Just look at the animation. Oops. So here you have k equals 3, and you have 3 cursors, red, green, and yellow. And as we are adding liquid, so as time goes by, you see that these cursors are going down. And let me take a moment here. So when I'm here, you see this red cursor is almost at the bottom of the bin. And look at where the other 2 cursors are. And if I run it and I stop it right here, it's the same thing translated 1 bin to the right. So this is a stationary liquid bin model. You can read it here. I'm not going full screen right now. So what we showed is that if you start from an arbitrary initial configuration, then the system converges exponentially fast to stationarity. So if you want to compute the speed, you just need to compute the speed at stationarity. So how do we do this? To every collection of parameters, A parameters and P parameters, we associate an assistance graph. It's a graph on k vertices encoding which cursors are in the same bin at some point during the stationary cycle. And it's called assistance graph because, so here you see that at this time, cursor number 2 is in the same bin as cursor number 1. So I'm adding an edge from 1 to 2 to materialize this. And if I continue running it, oops, bad. At this stage, cursor number 3 is in the same bin as cursor number 2. So I'm adding this edge between 2 and 3. But you see that at no point in the stationary cycle, 1, 2, and 3 are in the same bin, so there's no edge from 1 to 3.
So should the graph also be changing when removed?
So I look at an entire stationary cycle. And if there exists a time in the stationary cycle when they are in the same bin, then you add the edge.
So the graph is for the entire procedure,
Yes.
not for one instant?
No, not for 1 month, for the entire cycle.
Okay, thank you.
But there's only one stationary cycle, yeah?
Yes. It converges to the same stationary cycle. And it's called assistance graph because if you have this cursor number 1, it adds liquid to its right. And when cursor number 2 is in the same bin as cursor number 1, it's helping cursor number 1 to fill the bin to its right. So that's why it's called assistance graph. So that was one example. And now if I take different parameters, so the parameters were here, but please don't look at the numbers. If I take a different, oops, you get the news. a different collection of parameters. Is it a different one? Yes. So if you look carefully, you will see that cursor number 1 is always alone in its bin. So it has no edge to vertex number 2. And cursor 2 and 3 are sometimes in the same bin. So your graph is this. That's a different graph. So if I can take until 10, it's fine? OK. I'll wrap it up. So what you do is to each collection of parameters, you associate one assistance graph. So you have your parameter space, which is divided into regions indexed by assistance graphs. And we come up with a way of constructing a rational function associated to each assistance graph. It's an explicit construction, but a bit technical, so I'm not explaining it here. And this rational function only depends on the connected component of vertex 1 in the assistance graph. And what you observe is that you get a wall crossing phenomenon. It means that you have your parameter space with these parameters AI and PI, and it's divided into regions. On each region, your speed is a rational function of the parameters, but it's a different rational function in regions indexed by graphs that have a different connected component of the assistance graph. Let me show you an example. When you have two moves, so k equals 2, you have 4 parameters. But the PIs are summing to 1, so it removes 1 parameter. And you have some scaling property that if you multiply each AI by 1, then by lambda, then the speed gets divided by lambda. So you just need one A parameter. I can assume that A2 is equal to 1. So my phase space here is of dimension 2. And what you see is that you have this division. It's divided into 2 regions by this curve, which has this explicit equation. And the 2 regions, this region is indexed by this graph, assistance graph, and this one by this assistance graph. And here are the speeds of the front in each region. And you see that everything is very explicit. But actually, we have a similar explicit description for every size of the support of mu, not just 2. So here we have some explicit description. You can take 2 regions indexed by 2 assistance graphs, and you may ask, what is the dimension of their common boundary? So here is some explicit answer to this, but for time purposes, I'm not going to explain them. And these assistance graphs on k vertices, they are in bijection with Dyck paths of length 2k. So they are counted by Catalan numbers. And somehow, if you look at the regions, each region is indexed by a Dyck path. And if you look at the regions that are adjacent, separated by a wall meaning a boundary of codimension 1, and you can draw its dual graph. You connect 2 regions by a dual edge if they are separated by a wall. And what you obtain is something which is very well known. It's the Stanley lattice for Dyck paths. So it's some partial order on Dyck paths that say that one Dyck path is below another. You just draw them one on top of the other. That's the Stanley lattice for Dyck path. And that's what you get for the dual graph, of these adjacency of these regions. And we also have the explicit polynomial inequalities describing the boundaries between regions. And I finish with an open question because I've been growing up with this stratification of the Grassmannian and looking at cells and topological properties. So we proved that every region has non-empty interior. But here are 2 questions, topological question. Is every region connected? And is every region contractible? And that's all for me. And happy birthday, Rick.
Thank you, Sanjay, for a really nice talk. Do we have any So thank you for a really nice talk. Do we have any questions? Oh, Jim first.
I can wait for the mic, or I can just talk loudly.
It doesn't get on the top.
The mic is for recording.
Hi, thank you for that very nice talk. I think in all your examples of the assistance graph, it was just partitioning the numbers into contiguous blocks, in which case there would only be like 2 to the m minus 1 of them or something, not Catalan many. So what am I missing? I would have thought that if, I is adjacent to j, then they're both adjacent to everything in between in the assistance graph.
There is this nesting property about these graphs that, you see, when you have these cursors, if you have cursor I and j in the same bin, then I plus 1, I plus 2, I plus 3 is also in between, sandwiched in between. And because of that, these assistance graphs have this nesting property that if you have an edge from I prime to j prime, then any edge ij that is below it, that could be below it, is also in the graph. And because of that, it's counted by Catalan numbers and not 2 to the...
Any further questions?
So in the phase diagram, you said that there are these rational functions of p's and a's. Are they always continuous?
Yes.
But are they more? I mean, is it sometimes also differentiable across the boundary?
We haven't checked this.
Okay.
But basically, this is how you can get the equation of the boundary here. You just say this equals that.
Yeah, I mean, in this case, I
Yeah,
understand.
but in more general cases, the adjacencies are more complicated, so you need many inequalities, and it's not
Right,
obvious.
right. So it's not obvious if it's differentiable also across the boundary?
It's not obvious, and here it is not differentiable.
No, I know. Yeah.
But certainly, you could cook up some examples where it is differentiable, I guess.
So you mentioned your triangular sequences, right? Aren't they the same as parking functions, or are they
As what functions? Sorry?
parking functions? You know, where a bunch of cars park. They're not the same.
I don't know.
Yeah, but after you sort, it's going to be the same, right? Yeah. Okay. And then you have some summation. Oh, you have a formula for v sub mu, which is a sum over basically these triangular sequences. And yeah, this seems like an evaluation of some. There is a symmetric function which counts parking functions, and then this seems like an evaluation of that when you plug in mu instead of the variables, and then so that function has been studied for a while in McDonald theory, but you haven't looked at it, right?
Okay. Maybe
and also you have the Dyck paths which subdivide things into regions, and then there's a hyperplane arrangement where the parking functions appear as the regions inside of each Dyck path region.
Oh, the Dyck path, we have this, these infinite bin models indexed by mu, and then it's in the hydrodynamic limit, so it's not really within the realm.
Okay.
It's in a very special corner. This is a general formula for every mu.
Okay.
So I wouldn't put the Dyck path in here, but it would be interesting to see if at least for some mu's, you have some way to express it using parking functions.
Okay, thank you.
Okay. Are there any further questions for Sanjay?
Thank you for a very nice talk. I was just wondering, have you considered like the movement of the tallest bin?
Of the?
Of the tallest bin.
Tallest bin.
Because like I see that you are fixing the bin and then consider the length change, or like the front. What about like something?
I'm not sure I understand your question. You want to look at what is the highest bin at time t and track the position? No, I have no clue how to do that.
Okay, thanks.
So in your model, the ball which is being called is just replicating itself on the right.
Yes.
But what happened if it actually moved? So it moves to the right, but it's deleted. I mean, the original is deleted and it moves.
So in general, branching random walks, you will have a particle that reproduces, and reproducing means it is killed, and it creates some children around its position at a certain location. But you may allow general distributions of these children. So that's a very specific branching random walk, where the children, you put one children at the same place to replace the parent, and you add one child to its right, but you may define way more general branching random walk. So I think that's somehow what you're hinting at, maybe?
Yeah, I was just wondering if it's radically different, if it actually moves. So
Well, it's a different model, but it falls in the same class of branching random walks.
I see.
But I don't know about the behavior, because what we've studied here is very specific to this distribution of children, and if you change it, well, it breaks down.
Okay, thanks.
Okay, so maybe let's save further questions for the coffee break. Okay, so let's thank Sanjay again for the nice talk.